Faster-than-light travel is the ultimate fantasy of the stars. Every epic journey across the galaxy in stories we love is built upon this single, beautiful impossibility. Physics, as we know it, says no. The universe has a strict speed limit, and nothing carrying information or mass can ever cross it. This is the iron rule of Einstein's relativity, a cornerstone of modern science that has stood firm for over a century. Yet in 1994, a physicist named Miguel Alcubierre performed a breathtaking act of theoretical gymnastics. He wrote a paper that did not break the rules, but bent them into a new shape. He proposed a loophole, a method to travel faster than light without ever moving through space at all. This is the Alcubierre Metric, a warp drive blueprint written in the pure language of geometry. By the end of this exploration, you will understand not just the elegant mathematics of bending space-time, but the staggering physical price such a miracle would demand. We will uncover why this idea rekindled a scientific conversation many thought was closed, and what its profound obstacles reveal about the true fabric of reality. What does it say about our universe that its most tantalizing escapes are written in equations? Einstein's universe is built on a foundation of elegant and unyielding geometry. The speed of light is not merely a measurement, it is a fundamental property of spacetime itself, a constant woven into the very fabric of existence. In his theory of special relativity, Einstein revealed that as any object with mass moves faster, its energy requirements do not simply increase, they skyrocket towards infinity. To push a single proton to the speed of light would demand more energy than exists in the entire observable universe. This is the ultimate roadblock, a cosmic traffic law written into the geometry of reality. It means the stars, for all their beauty, are fundamentally isolated. A journey to our nearest stellar neighbor, Proxima Centauri, would take over 4 years traveling at light speed, and for any ship with mass, that trip is forever out of reach. This creates the central paradox of our interstellar dreams. To make the galaxy accessible within a human lifetime, we must find a way to travel effectively faster than light, but without ever locally breaking that sacred speed limit. We must respect Einstein's rules while finding a loophole written in the same language he used to define them, the language of curved spacetime. The challenge is not to build a faster engine, but to reimagine the road itself. The concept of a warp drive feels like a gift from science fiction, a piece of future technology beamed directly into our collective imagination. In shows like Star Trek, it was presented as a solved problem, a hum of the engines and a streaking of stars as the ship entered a realm beyond normal space. For decades, audiences understood it simply as going very, very fast. But the fictional warp drive held a seed of a much deeper truth, one that physicists would later recognize. It wasn't about velocity in the traditional sense. The characters weren't accelerating a massive starship through the vacuum. They were doing something far more profound. They were manipulating the stage upon which the drama of motion unfolds. They were altering spacetime itself. This subtle but monumental shift in thinking is what separates a naive fantasy from a genuine theoretical proposal. The real breakthrough wasn't imagining a faster rocket, it was asking a different question entirely. What if, instead of moving the ship, you could move the space containing the ship? Picture a moving walkway at an airport. You stand still on the walkway, yet relative to the static floor, you are carried forward. A warp drive aims to create a similar effect, but the walkway is the fabric of the universe. The ship rests inside a self-contained bubble of normal spacetime, a safe pocket for its crew and physics. Then, the spacetime in front of the bubble is contracted, squeezed together like the folds of an accordion. Simultaneously, the spacetime behind the bubble is expanded, stretched out. The bubble and everything inside it, is then carried along this artificial wave in the geometry of reality. Crucially, within the bubble, the ship is motionless. It feels no acceleration, experiences no time dilation from high speed, and most importantly, it never locally exceeds the speed of light through the space immediately around it. The bubble itself, however, the boundary between compressed and expanded spacetime, can in theory propagate at any speed, limited only by the mechanics of creating the distortion. This is the breathtaking leap from science fiction trope to formal physics. It transforms the problem from one of propulsion and fuel to one of geometry and gravity. The question is no longer how fast can we push something, but how do we sculpt the invisible fabric that everything is embedded within? This geometric reimagining found its formal voice in the work of a Mexican theoretical physicist named Miguel Alcubierre. A self-professed fan of science fiction, Alcubierre was captivated by the same paradox that taunts every starry-eyed dreamer. He saw the ironclad rule of light speed, and instead of asking how to break it, he asked a more clever question. Could the universe's own rules provide a detour? In 1994, he published a paper in the journal Classical and Quantum Gravity that would become legendary. Its title was straightforward: The Warp Drive Hyperfast Travel Within General Relativity, but its approach was revolutionary. Alcubierre did not propose a new type of engine or a magical fuel. He treated the concept of a warp drive with utter seriousness, as a purely geometric problem. His key insight was to frame it not as science fiction, but as a specific mathematical solution to Einstein's own field equations. These are the core equations of general relativity that describe how matter and energy tell spacetime how to curve. What Alcubierre did was work backwards. He started with the desired outcome, a bubble of flat spacetime moving at an arbitrary speed, and then asked what arrangement of matter and energy would be required to produce that specific curvature. The result was the Alcubierre Metric, a precise mathematical description of a spacetime geometry that allows for effective faster-than-light travel. This was no mere speculation. It was a formal exercise in the language of the cosmos itself. It demonstrated that, in the abstract realm of geometry, such a thing was not forbidden. The paper was a masterstroke, elevating a fantasy trope into a legitimate, if profoundly challenging, subject for theoretical physics. It proved that the dream of the stars could be written in the same elegant script that describes black holes and the expanding universe. Alcubierre's metric translates that elegant geometry into a precise set of instructions for reality. The core mechanism is deceptively simple in concept, yet unimaginably complex in execution. To create a warp bubble, you must engineer a very specific distortion in the fabric of spacetime directly around your vessel. Picture space not as an empty void, but as a stretchable rubber sheet. Now, imagine taking the region of that sheet immediately in front of your ship and forcefully compressing it, pulling distant points closer together. Simultaneously, you would take the region of the sheet directly behind your ship and stretch it outward, making the space there longer. Your ship sits in a pocket of perfectly normal, flat spacetime between these two manipulated zones. This is the warp bubble, a stable island of familiar physics in a sea of artificial curvature. Because space itself is contracting in front and expanding behind, the bubble is pushed forward on this wave of geometry. It is like a surfer being carried by an ocean wave. The surfer does not paddle to match the wave's speed. They are lifted and propelled by the water's own motion. Inside the warp bubble, the ship is that surfer, motionless relative to the immediate water, yet hurtling forward relative to the distant shore. This is the brilliant loophole. The ship's speedometer reads 0. No part of the vessel or its crew ever moves faster than light through the local space inside their pocket. But to an observer watching from a distant star, the entire bubble, and the ship within it, would appear to vanish from one point and reappear at another faster than a beam of light could make the same journey. The distance it effectively covers is not a measure of its engine thrust, but of how severely you can scrunch the universe ahead and stretch it behind. The travel time between stars becomes a question of geometry, not velocity. You are not breaking the cosmic speed limit, you are cleverly redrawing the map so the destination is brought to you. The beauty of Alcubierre's proposal lies in its mathematical clarity. To understand it, we do not need to solve complex equations ourselves, but to appreciate the story those equations tell. The metric itself is a kind of cosmic recipe, with each ingredient describing a specific part of the warp bubble structure. At its heart, the recipe begins with a familiar base, the Minkowski metric. This is the mathematical description of perfectly flat, empty spacetime, the calm and uneventful void of deep space far from any star or planet. Inside the warp bubble, this is exactly the environment the ship experiences. The crew lives in a pocket of normal physics, where time flows at its usual rate and distances are what they appear to be. This is the first crucial ingredient, ensuring the journey is not just fast but survivable. The second ingredient is the warp function, often represented by a simple mathematical term. This function is the architect of the distortion. It does two jobs simultaneously. First, it defines the shape and size of the bubble. It tells spacetime exactly where to begin contracting in front of the ship and where to begin expanding behind it, creating a smooth, stable boundary around that central pocket of flat space. Think of it like drawing a circle on that rubber sheet, marking the exact area you intend to manipulate. Second, and most importantly, the warp function encodes the bubble's velocity. By adjusting a single parameter within this function, Alcubierre could mathematically dial the bubble's speed from a slow crawl to many times the speed of light. The function essentially programs the severity of the spacetime compression and expansion, which directly dictates how fast the wave will carry the bubble forward. When these two ingredients are combined within the framework of Einstein's equations, they yield the complete Alcubierre metric. This final formula is a full geometric description of the entire system, the distorted spacetime landscape. It mathematically guarantees that an observer inside the bubble feels no acceleration, experiences no time dilation from high-speed travel, and is protected from the extreme curvature just outside their window. The metric treats the bubble as a self-contained object moving through spacetime, not as a ship moving through space. This distinction is everything. It transforms a journey between stars from a marathon through a vast distance into a controlled manipulation of distance itself. The equations present a vision where travel time is not governed by thrust, but by geometry, a vision written in the pure language of relativity. Yet, as elegant as this recipe appears, reading it reveals a shocking list of required ingredients that may not exist in our universe. The magic of Alcubierre's design lies in a single, powerful mathematical tool called the warp function. This is not a physical component you could touch, but the precise instruction set that tells spacetime exactly how to bend. It defines the very shape and behavior of the warp bubble. Think of it as the architect's blueprint for the distortion. The function creates a smooth, continuous transition between the bubble's perfectly flat interior and the wildly curved exterior. It carves out a safe pocket for the ship, a region where spacetime remains normal and calm, as if the immense distortion outside simply does not exist. This pocket is encapsulated by a thin shell, a boundary wall of intense curvature. On one side of this wall, inside the bubble, physics operates as we know it. On the other side, space is either severely compressed ahead or dramatically expanded behind. The wall itself is where the geometry changes, a narrow band of transition where the rubber sheet of the universe is either being pulled tight or stretched thin. The elegance of the warp function is that it controls everything. By adjusting its parameters, you can mathematically dictate the size of the bubble, the thickness of this boundary wall, and most astonishingly, the bubble's effective velocity. You can set the function to describe a bubble moving at a walking pace, or one moving at 10 times the speed of light. The velocity is not a result of acceleration. It is baked directly into the geometry from the start. The function programs the severity of the spacetime compression and expansion, and that programming determines how fast the wave will carry the bubble forward. In the pure language of mathematics, this allows for an arbitrarily high speed. The equations place no upper limit. This is the source of both the idea's thrilling promise and its deepest, most troubling implications. For if the geometry permits any speed, then what must we use to sculpt that geometry? The answer lies in a form of energy so strange, it seems to defy the intuitive rules of our universe. The elegance of the warp function, however, conceals a staggering physical demand. To sculpt spacetime in the way Alcubierre's blueprint requires, you need a very special kind of ingredient, one that does not behave like anything we find in our everyday world. Einstein's equations show that the specific curvature of a warp bubble, with space compressed in front and expanded behind, cannot be generated by ordinary matter. Normal matter, everything from stars to dust to our own bodies, has what physicists call positive energy density. It creates the kind of gravity we are familiar with, the kind that attracts, that pulls spacetime inward in a gentle curve around a planet or a star. But to contract space in front of the bubble, you need a form of gravity that repels, that pushes spacetime together. To expand space behind it, you need that same repulsive effect. This requires the opposite of normal matter, something with negative energy density. Physicists often call this exotic matter. It is not a new element on the periodic table, but a hypothetical form of energy that would exhibit negative pressure. Think of it like a kind of anti-gravity cement. While normal matter makes the rubber sheet of spacetime sag downward, exotic matter would make it bulge upward, creating the precise contours needed for the warp bubble's walls. This requirement is not a minor engineering detail. It is a fundamental consequence of the geometry. The Alcubierre metric is mathematically valid only if you can line the interior of that warped shell with this exotic substance. Without it, the beautiful bubble of the equation simply cannot be physically assembled. It is the first and perhaps greatest hurdle, because this exotic matter, if it can exist at all, violates what are known as the classical energy conditions. These are bedrock principles that all normal matter and energy obey, rules that ensure gravity always attracts and that energy densities are never negative. To build a warp drive is to ask the universe to temporarily suspend one of its most fundamental behaviors in a controlled, macroscopic way. It is the difference between drawing a beautiful castle on paper and being told you must build its foundation from a material that actively pushes away from the Earth. The dream of bending spacetime collides head-on with the apparent rules of what is allowed to exist within it. Exotic matter sounds like a substance from the farthest reaches of speculative fiction, but its theoretical roots are surprisingly concrete. It is crucial to understand what it is not. Exotic matter is not antimatter. Antimatter, while rare and fascinating, still possesses positive energy density. When an electron meets its antimatter counterpart, a positron, they annihilate in a burst of pure energy. That energy is positive. Antimatter obeys the same classical energy rules as normal matter. It simply has an opposite charge. Exotic matter is something else entirely. It is a hypothetical form of energy that would exhibit a negative energy density. This means its presence would create a gravitational effect opposite to everything we know. Instead of attracting, it would repel. It would make the fabric of spacetime bulge outward rather than sag inward. This is the anti-gravity cement required to mold an Alcubierre warp bubble. lining its walls to create the precise contours of compressed space ahead and expanded space behind. The concept seems to violate the intuitive rules of our universe, and for large, stable quantities it likely does. Yet, physics offers a tiny, tantalizing loophole at the quantum scale. The vacuum of space, according to quantum field theory, is not truly empty. It is a seething, bubbling foam of virtual particles that constantly wink into and out of existence. These fleeting fluctuations create a background energy, and under certain conditions, this can be manipulated to produce a measurable negative pressure. The clearest demonstration of this is the Casimir effect. Imagine placing two perfectly smooth, uncharged metal plates extremely close together in a vacuum. The quantum fluctuations between the plates are restricted, while those outside the plates are not. This imbalance creates a net force that pushes the plates together. From a certain perspective, the region between the plates can be said to have a lower energy density than the surrounding vacuum, effectively a negative energy density relative to the baseline. This is not exotic matter you could scoop into a container, but it is a real, laboratory-tested phenomenon where the geometry of boundaries induces a quantum effect that aligns with the theoretical requirements for exotic energy. It proves that, on a microscopic scale, the universe does permit these strange energy states. The problem for a warp drive is one of astronomical scale. The Casimir effect produces a force measurable only at nanometer distances. The negative energy required to stabilize a macroscopic warp bubble for a spaceship is many, many orders of magnitude greater. We are talking about the difference between the gentle push that makes two tiny plates touch and the force needed to crumple the fabric of spacetime itself across interstellar distances. Bridging that gap is the monumental challenge. It asks whether a quantum whisper can be amplified into a geometric roar. The scale of the energy required is almost beyond human comprehension. Early calculations based on Alcubierre's original metric delivered a sobering, even shocking result. To create a warp bubble just a few hundred meters across, moving at 10 times light speed, you might need an amount of negative energy equivalent to converting the entire mass of Jupiter into pure energy. Not just the planet's physical matter, but its total mass energy, a number with over 27 zeros in joules. Some later refinements suggested the requirement could be reduced, perhaps to the mass of a small moon, but even that represents energy far beyond any technology we can conceive of harnessing. The most extreme interpretations were even more daunting, suggesting the necessary negative energy density might be comparable to the total mass energy contained within the entire visible universe. These figures are not meant to crush the dream, but to illustrate a fundamental truth. Warping spacetime on a human scale is not a gentle act. It is an intervention of cosmic proportions, a demand to rearrange the deepest geometry of reality itself. The energy problem highlights that the universe does not offer such profound shortcuts cheaply. It places the warp drive concept squarely in the realm of what physicist Michio Kaku might call a Type 3 civilization technology, something achievable only by a society that has mastered the energy output of an entire galaxy. This transforms the challenge from a simple engineering puzzle into a question about the ultimate limits of physical possibility and control. Beyond the staggering energy requirements lies an even stranger consequence, one that touches the fundamental nature of cause and effect. The intense curvature of spacetime at the warp bubble's boundary wall may not be a smooth, gentle slope. Some analyses suggest it could become so severe that it forms an event horizon. This is not the vast horizon of a black hole, but a smaller, artificial one, wrapping the bubble like a shimmering, impassable shell. An event horizon is a point of no return in spacetime, a boundary beyond which nothing, not even light, can escape. If such a horizon formed around the warp bubble, the crew inside would be permanently trapped. They could fly their bubble across the galaxy, but they could never turn it off, never step outside, and never communicate with the universe they left behind. They would be prisoners in a self-made geometric cage, carried along on a wave they could no longer control. This turns the dream of exploration into a paradox of isolation. But the implications run even deeper into the very logic of time itself. The real theoretical danger of a warp drive capable of faster-than-light travel is not isolation, but the potential to break causality. In our universe, cause must always precede effect. You cannot hear the sound of a bell before it is struck. This logical flow is woven into the geometry of spacetime by the speed of light, which sets the maximum speed for any signal or influence. If you could travel faster than light, even effectively through a warp bubble, you could, in principle, outrun a light beam. By taking a shortcut through warped space, you could arrive at a distant star before a light signal announcing your departure had even gotten there. To an observer at that star, you would appear to have arrived before you left. With careful maneuvering between different warp paths, some physicists have shown it might be possible to create a closed time-like curve, a path through spacetime that loops back on itself, allowing a traveler to return to their own past. This is the realm of time travel paradoxes, where you could potentially meet your earlier self or alter an event that has already happened. Such possibilities create profound conflicts with our understanding of physics, suggesting that the laws of the universe might not allow for stable warp geometries that permit faster-than-light travel, simply to protect the consistent flow of time. The universe may enforce causality as a cosmic law, making any geometry that threatens it inherently unstable or impossible to construct. This suggests the ultimate limit on a warp drive may not be our engineering skill, but the universe's own need for a coherent story where every effect has a clear preceding cause. The profound challenges of Alcubierre's design did not end the conversation, they refined it. A decade after that groundbreaking paper, another physicist offered a different geometric path. In 2001, José Natário, building on the same foundation of general relativity, proposed an alternative model for a warp drive. His approach was subtle but significant. Instead of requiring spacetime to actively compress in front of the bubble and expand behind it, the Natario drive relies on what is called a shearing motion. Picture the warp bubble not as a surfer on a moving wave of water, but as a fixed point on a rotating disk. The space around the bubble is not pushed or pulled, but is set into a smooth, swirling flow. Points of space directly in front of the ship slide sideways around the bubble's edges, smoothly rejoining the flow behind it. The bubble itself remains perfectly motionless within this moving stream of spacetime geometry. From the outside, it appears to translate forward, but internally, nothing moves. There is no expansion of space behind the vessel, eliminating one of the more extreme geometric manipulations of the Alcubierre model. This shearing flow is mathematically elegant, and it offers a potential safety advantage. Without a region of violently expanding spacetime in its wake, a Natario drive might avoid creating the dangerous horizons and radiation that could plague an Alcubierre bubble. The journey could be far smoother for both the ship and the spacetime it passes through. Yet, for all its geometric refinement, the Natario drive still confronts the same fundamental barrier. It, too, requires exotic matter to generate and sustain that precise shearing flow of spacetime. The walls of its bubble must be lined with negative energy density to sculpt the geometry of motion. Early analyses suggested its energy requirements might be similarly astronomical, perhaps even more so than the original Alcubierre metric. So while Natario's work demonstrated that the warp drive concept was not a single, fixed idea, but a family of geometric possibilities, it did not provide an escape from the core dilemma. It showed that bending spacetime for travel, in any stable, controlled form, seems inextricably linked to the need for a substance that defies the ordinary rules of our universe. The dream persisted, but the price remained cosmic. The search for a physical warp drive, therefore, seems to hinge on a profound dilemma. We must either find a cosmic quantity of a substance that may not exist, or we must accept that our interstellar dreams are forever confined to geometry on a page. But theoretical physics rarely accepts a dead end. In recent years, researchers have begun probing a more subtle possibility, one that shifts the goal from finding exotic matter to engineering the very fabric of the void. The key lies not in a substance but in a state, the quantum vacuum. This is the seething, energetic foundation of all reality, not truly empty, but filled with transient fluctuations and virtual particles. The question becomes, could we manipulate this vacuum itself to produce the needed warp geometry? Could we polarize the void, much like we polarize a material, to temporarily exhibit the properties we need? This line of inquiry moves beyond simply requiring exotic matter to asking if we can induce a similar effect through clever configuration of boundaries and fields, leveraging phenomena like the Casimir effect on a grand, controlled scale. It is the difference between mining for a magical mineral and learning to program the background energy of the universe. The concept is known as vacuum polarization. In strong electromagnetic fields, like those near a massive charged object, the quantum vacuum can become polarized. Virtual particle pairs, which normally wink in and out of existence randomly, become influenced by the field. They align, effectively becoming tiny dipoles, and this alignment changes the local properties of the vacuum. It modifies how energy and pressure behave in that region. The tantalizing suggestion from some theoretical models is that by creating and arranging immensely powerful, structured fields, we might be able to polarize the vacuum around a spacecraft in just the right way. This polarization could, in principle, generate regions of negative energy density as a dynamic byproduct of the field's interaction with the quantum foam, rather than as a pre-existing bulk material. Think of it not as building a wall of exotic bricks, but as using a powerful, shaped magnet to temporarily rearrange iron filings into the shape of a wall. The filings are not inherently magnetic walls, but under the right influence, they act as one. The quantum vacuum could be those filings. The required fields are still far beyond our capabilities, and the calculations are immensely complex, but this reframes the problem in a potentially more tractable way. It suggests the warp bubble might not be a static structure built from impossible materials, but a dynamic, sustained pattern, a standing wave in the quantum fields of spacetime itself. The energy to create and hold that pattern would still be astronomical, but the source shifts from a mythical substance to the manipulation of fundamental forces. This is the frontier where warp drive theory meets quantum field theory, a convergence that asks if the ultimate engine for crossing the stars might be one that carefully tunes the hum of empty space. The Alcubierre warp drive is not alone in its geometric ambition. It belongs to a small, fascinating family of theoretical structures, all conceived to outwit the cosmic speed limit by re-engineering the very stage of reality. These are not competing ideas so much as different blueprints drawn from the same set of universal rules, each offering a distinct path through the folded fabric of spacetime. Alongside the warp bubble, two other concepts stand out, each with its own compelling and problematic geometry. The first is the traversable wormhole, often visualized as an Einstein-Rosen bridge. Picture the universe not as a flat sheet, but as a three-dimensional volume. Now, imagine taking two distant points on this volume and pinching them together, then punching a tunnel through the pinched connection. This tunnel, or throat, would create a shortcut, a cosmic subway linking places that are otherwise light years apart. A ship would enter one mouth of the wormhole and emerge almost instantly from the other, having traversed a manageable distance through the tunnel while effectively crossing an interstellar gap. The geometry is elegant, a solution to Einstein's equations that connects two separate regions of spacetime. but like the warp drive, its stability comes at a cost. To keep the throat from pinching shut instantly, which the equations say it wants to do, you would need to line its interior with exotic matter. This negative energy would act as a kind of scaffolding, propping the tunnel open against the crushing weight of its own geometry. The requirements are, once again, astronomical, and the wormhole presents its own unique perils. Anything passing through could trigger destructive feedback, collapsing the tunnel, or the very act of trying to traverse it might destabilize the connection. Both the warp drive and the wormhole share this core dependency, a need for exotic energy to sculpt and sustain a stable shortcut. The second member of this family is a less famous but equally ingenious concept, the Krasnikov tube. Proposed by physicist Sergei Krasnikov in the 1990s, this idea approaches the problem from a different angle. Instead of moving a bubble or creating a tunnel, the Krasnikov tube is about modifying a pre-existing path. Imagine a crew embarking on a slow, sub-light-speed journey to a distant star. As they travel, they could, in theory, deploy a technology that permanently alters the spacetime along their route. This process would create a tube-like region where space behind the ship is compressed, effectively shortening the return journey. The crucial feature is that this tube is a one-way modification. The outgoing trip is still slow, but the return through this pre-compressed spacetime corridor could be nearly instantaneous. It functions like a cosmic subway line laid down during the initial voyage. The appeal is that it avoids some of the causality problems of warp drives, as the tube is constructed at sub-light speeds, yet it too faces monumental hurdles. Creating a permanent, macroscopic distortion in spacetime along a light-year-long path would demand a staggering and continuous output of energy, likely requiring exotic matter to stabilize the tube walls. Furthermore, the tube only benefits those coming back along the exact same path, making it a monumental infrastructure project for a single route. What unites these three ideas, the warp bubble, the wormhole, and the spacetime tube, is a shared language of geometry and a shared reliance on physics that pushes against the classical rules of our universe. They all demonstrate that within the elegant framework of general relativity, pathways to the stars are mathematically conceivable. Their blueprints are written in the cosmos's own script. Yet each one, when we ask how to build it, points to a requirement for energies and substances that seem to belong to a different order of reality. This is the profound pattern. The universe's rulebook allows for the drawings of these magnificent bridges and tunnels, but it may have hidden the construction materials in a vault we cannot yet open. The challenge shifts from proving something is geometrically possible to discovering whether our universe permits it to be physically assembled. This brings us to the most practical question of all. If we cannot find exotic matter, is there any other way to bend the rules? Theoretical blueprints are one thing, but to know if a warp bubble could truly exist, we must see it in motion. This is where the equations leave the page and enter the supercomputer. A field called numerical relativity has become the essential proving ground for these ideas. Unlike traditional analytical relativity, which seeks exact, elegant solutions to Einstein's equations, numerical relativity embraces their immense complexity. It treats spacetime not as a static geometry, but as a dynamic, evolving entity, a fabric that can be modeled as a vast, intricate grid. Think of it like a cosmic weather simulation. Just as meteorologists divide the atmosphere into millions of cells to model a hurricane's formation and path, numerical relativists divide a region of spacetime into a computational mesh. They program in the initial conditions the starting shape of a hypothetical warp bubble, and then let the laws of physics coded into algorithms dictate what happens next. They press play on the universe itself in a controlled digital environment. This allows them to test the stability of an Alcubierre or Natario metric over time, to see if the beautiful balanced geometry of the initial snapshot can hold itself together, or if it will inevitably collapse, twist, or transform into something else. It moves the question from, is this mathematically allowed, to, would this physically last? The answers from these simulations are both illuminating and sobering, revealing hurdles that pure algebra could not foresee. When researchers simulate a warp bubble's journey, they often observe a troubling phenomenon. As the bubble moves through space-time, it does not simply glide through a passive void. It interacts with the quantum fields that permeate all of existence. Particles and energy, even in the deepest vacuum, are not completely swept aside by the bubble's walls. Instead, simulations suggest that quantum fields can become trapped and focused directly in front of the leading edge of the warp bubble. Imagine a boat plowing through a misty lake. Water droplets don't just part, some collect on the bow, building up. In the warp bubble's case, it's not water but energy and particles that accumulate. This isn't a gentle buildup. The geometry of the warp drive compresses this accumulating energy into an increasingly dense, focused region right at the bubble's forward boundary. The simulations show this energy density growing without an apparent upper limit as the bubble continues its journey. The result is a mounting wall of radiation and high-energy particles, a cosmic snowplow blade of intense energy forming just ahead of the ship. For anything inside the bubble, this presents a catastrophic problem. When the journey ends and the warp field is deactivated, that accumulated energy wall would not simply vanish. It would likely flood into the bubble's interior or be released in a devastating burst. The ship and its crew, having traveled safely in their pocket of flat spacetime, would be confronted with the entire accumulated energy of their interstellar voyage, delivered all at once at their destination. This isn't just a navigation hazard, it's a fundamental interaction between the warp geometry and the quantum texture of the universe, suggesting that even if you could build the drive, you might not survive turning it off. These computational experiments reveal a deeper principle. The universe seems to resist shortcuts with hidden costs. The warp drive geometry, while elegant in a snapshot, appears to have natural instabilities when set in motion. Some simulations indicate that the negative energy shell required to sustain the bubble might be inherently unstable over time. Tiny fluctuations, inevitable in any real system, could cause the shell to oscillate, buckle, or even disintegrate, collapsing the delicate bubble and leaving the ship stranded in normal space. Other analyses suggest that creating a warp bubble from a standstill, the process of forming the geometry in the first place, may already require the ship to be moving at a significant fraction of light speed, a classic chicken and egg problem for a technology meant to bypass that very limit. Perhaps most intriguingly, the simulations force us to consider the bubble's interaction with the universe it passes through. A warp bubble moving faster than light would generate a kind of sonic boom in spacetime, a shockwave of gravitational radiation and particles. This would not be a stealthy technology, it would be a spectacularly disruptive event, leaving a permanent, detectable signature in the fabric of the cosmos. The act of passage itself would alter the space it traveled through. This shifts the perspective from a simple engineering challenge to an ecological one. It asks whether the space-time we live in can tolerate such severe, localized manipulations without responding in ways that make the journey impossible or the destination unrecognizable. The simulations don't yet provide final answers, but they are refining the questions, transforming science fiction dreams into precise, computable problems in theoretical physics. They show us that the path to the stars, if it exists, is not a straight line on a map, but a delicate negotiation with the dynamic, living geometry of reality itself. A warp drive would not be a silent ghost slipping between the stars. It would be a thunderclap in the fabric of reality, announcing its presence with forces that reshape everything in its path. The extreme curvature of spacetime at the bubble's boundary is not a static sculpture, it is a dynamic, moving distortion. As this massive warp in geometry propagates faster than light, it would generate gravitational waves of unimaginable intensity. These would not be the faint ripples detected from colliding black holes, but titanic tsunamis in spacetime itself. To any planet or star system lying even remotely near its course, the passing bubble would deliver a gravitational shockwave. It could trigger cataclysmic tectonic events, destabilize orbits, and strip atmospheres away with the sheer force of its distortive wake. The drive's path would etch a scar of gravitational turbulence across light years, a permanent testament to its passage. This transforms the dream from a simple voyage into an act of profound cosmic alteration, raising an ethical question for any civilization that could wield it. Does the right to explore include the right to permanently rearrange the galaxy behind you? The gravitational disturbance is only the beginning of the external effects. Recall the simulations showing quantum fields piling up at the front of the bubble. This is not a minor accumulation. As the bubble moves, it would sweep up every stray hydrogen atom, every dust particle, every bit of interstellar medium in its path. These particles cannot cross the warp bubble's boundary, so they become trapped, compressed by the geometry into a denser and denser region directly ahead of the ship. For a vessel traveling at many times light speed, even the sparse hydrogen of the galactic void would be collected at a ferocious rate. The result is a lethal buildup. The trapped matter, subjected to insane pressures and energies from the warp field's leading edge, would be heated into a searing plasma, a wall of radiation and high-energy particles riding just in front of the bubble. This is the warp shock, a bow wave of pure destruction. Its intensity would grow throughout the journey, meaning the longer the trip, the more deadly the accumulated front becomes. Any celestial body, from an asteroid to a planet, that happened to lie on the bubble's trajectory would not simply be passed by. It would be struck by this concentrated blast of everything the warp drive had collected across light years, a cosmic shotgun blast moving at superluminal speed. The ship inside the bubble might be safe from the immediate radiation, but it would be piloting a weapon of mass destruction, with its target being its own destination. This leads to the profound and often overlooked problems of navigation and termination. Steering a warp bubble is not like turning a car. You are not pivoting a vehicle within space, you are attempting to redirect the shape of spacetime itself. The geometry of the bubble is a precise, balanced structure. To change course, you would need to dynamically reconfigure the entire warp field, shifting the regions of compression and expansion in a controlled manner. The energies involved in such a maneuver would be astronomical, and the gravitational and particle shockwaves generated by the turn would be even more complex and violent, potentially lashing out across a wider swath of the cosmos. But the greater challenge might be stopping. How do you safely dissolve a warp bubble? You cannot simply cut power. The moment the exotic matter scaffolding is removed, the intricate geometry sustaining the bubble would collapse. All that spacetime curvature, held in check by negative energy, would snap back to its normal, flat state. The consequences of this sudden geometric release are terrifying to consider. First, the deadly plasma shock front accumulated during the journey would no longer be held at bay by the warp field's boundary. It would likely flood into the region the ship now occupies, engulfing it in a firestorm of its own making. Second, the collapse of such a massive, moving curvature would itself release an enormous burst of energy, a final gravitational pulse that could devastate the local space around the arrival point. You might successfully travel 100 light-years only to annihilate your destination star system upon arrival. This suggests a warp drive may not be a controllable engine in the traditional sense, but more like a geometric bomb you carefully ignite and then hope to survive the detonation of. The universe seems to demand a reckoning for the shortcut, presenting a bill paid in radiation and gravitational chaos that must be settled at the journey's end. Accelerating a warp bubble presents a paradox hidden within its own geometry. The mathematics of the Alcubierre metric allows you to define a bubble moving at any speed, from a slow drift to many times light speed, but it describes only a steady state. It is a snapshot of a bubble already in motion. The equations are silent on how you get it there. This is the problem of the warp trigger, the transition from standing still to moving faster than light. Is it a smooth ramp up, or does it demand an impossible surge of power at the moment of crossing light speed? Some early analyses suggested a terrifying possibility. As the bubble's velocity approaches the speed of light from below, the energy required to sustain its geometry might not just be large, it might become infinite. This would create an impassable barrier, a sort of warp sound barrier, where the energy cost to push just a little faster diverges to an impossible value. It would mean that while a superluminal bubble can exist in theory, you could never accelerate one to that speed starting from rest. You would be forever stuck in the subluminal regime, making the technology a very complex way to travel slower than light. This is reminiscent of the classic relativistic problem for objects with mass, where their energy requirement blows up to infinity as they approach light speed. The warp drive was supposed to bypass that, but its own geometry might impose a similar, perhaps even more severe, restriction on the process of acceleration itself. The issue centers on the region of space just in front of the bubble, the area being compressed. As the bubble's speed increases, this compression becomes more severe. To maintain that increasingly sharp curvature dynamically, the exotic matter lining the bubble walls might need to be configured with ever more negative energy density. The calculations indicated that at the exact moment of crossing the light speed threshold, this requirement could become singular, demanding an infinite amount of negative energy. If true, the warp barrier is not just an engineering challenge, it is a fundamental geometric dead end. However, more recent dynamical studies offer a sliver of hope. By modeling the warp bubble not as a static picture but as an evolving structure in time, researchers have explored what are called dynamical solutions. These computer simulations treat the warp field like a fluid that can be gradually shaped. In some of these models, the transition might be managed without an infinite energy spike. The key is in how you configure the initial warp field. Instead of trying to push a fully formed bubble faster and faster, you might start with a very wide, gentle distortion in spacetime. This distortion would initially propagate at subluminal speeds. Then, by carefully adjusting the distribution of energy that creates the field, you could slowly tighten the bubble, focusing the curvature and allowing the wave peak to steepen. In this gradual process, the bubble's effective speed could increase smoothly. The moment of crossing light speed in these simulations does not necessarily show a catastrophic singularity. It appears as a continuous parameter change within the equations governing the field's evolution. Think of it like forming a wave on the surface of a pond. You don't start with a perfect breaking wave. You create a broad swell, and then by adding more energy in just the right way, you can focus that swell into a taller, sharper peak that moves faster. The dynamical approach suggests the warp trigger might be less about brute force acceleration and more about the precise, gradual sculpting of a spacetime wave from its very inception. Yet, even if the energy requirement remains finite, another profound issue emerges during this transition: the potential formation of an event horizon. As the bubble's wall steepens and its speed increases, the spacetime curvature at its boundary becomes more extreme. There is a critical point where this curvature could become so severe that it forms a closed, trapped surface. This is a region where all light rays, and therefore all possible paths, point inward. It becomes an event horizon, encapsulating the entire bubble. For the crew inside, this would be a point of no return in a deeply unsettling way. Once the horizon forms, they would be causally disconnected from the universe outside. They could no longer send signals out, receive information in, or, most critically, turn off the warp drive. Any command to disengage the field could not cross the horizon outward to affect the apparatus creating it. They would be locked in a geometric prison, hurtling forward on a course they could no longer alter or cease. Their journey would become a one-way trip into permanent isolation. This risk suggests that a controllable warp drive must be carefully operated far below the threshold where such horizons naturally form, which might inherently limit its maximum speed to values still below light speed. The dream of a smooth acceleration to superluminal travel is thus hemmed in by two towering cliffs, the chasm of infinite energy and the wall of causal isolation. Navigating between them requires a control over space-time geometry so exquisite, it approaches the artistry of a cosmic sculptor, working with materials whose full nature we have yet to comprehend. Perhaps the most pragmatic path forward lies not in chasing superluminal dreams, but in mastering a slower, more deliberate geometry. Subluminal warp drives represent a fascinating middle ground, a theoretical stepping stone that asks a more immediate question. What if we could manipulate spacetime to achieve a significant fraction of light speed, say 99.9%, without ever firing a traditional rocket? The concept is identical in form to the Alcubierre metric, but with the velocity parameter dialed down. Space is still compressed ahead of the bubble and expanded behind it, creating that same geometric wave. The ship still rides motionless within its pocket, but the wave itself propagates at a speed less than that of light. This eliminates the most profound theoretical headaches. There are no closed time-like curves, no violations of causality, and the risk of forming an event horizon around the bubble diminishes greatly. The journey from a physics standpoint becomes far cleaner, a dramatic demonstration of geometric propulsion without the paradoxes. Yet, this apparent simplification does nothing to ease the monumental physical requirements. A subluminal warp bubble still demands the same exotic matter scaffolding, the same negative energy density lining its walls to create the curvature. The energy needed might be slightly less than a superluminal version, but it remains astronomically, prohibitively high. You are still asking the universe to let you mold its fabric on a macroscopic scale, and it still presents a bill written in a currency we do not possess. So why even consider it? The value is not in immediate practicality, but as a profound proof of concept. Detecting or creating even a microscopic, incredibly slow warp distortion in a laboratory would be one of the most significant discoveries in the history of physics. It would prove unequivocally that the geometry described by Einstein's equations can be intentionally engineered. It would move the warp drive from a page of mathematics into the realm of observable phenomena, however faint. Such an experiment would not send a ship to Alpha Centauri, but it would illuminate the path. It would transform our understanding of gravity from a force we merely observe to a field we might one day sculpt. Mastering a subluminal warp drive, even a tiny, crawling one, would teach us the control language of spacetime itself, the first stumbling steps in a grammar of cosmic engineering. The most dangerous part of the journey is not the destination, but the wall you must build to get there. This is the bubble wall, the razor-thin boundary separating the calm, flat spacetime of the ship's interior from the violently distorted geometry outside. It is not a physical barrier you can touch, but a region of such extreme curvature that the very rules of physics stretch to their breaking point. Within this microscopic shell, space is not merely bent, it is under titanic tension. Picture a sheet of rubber being pulled in opposite directions with unimaginable force. On one side, the sheet is being compressed into a tight knot. On the other, it is being stretched into a thin film. The wall is the transition zone between these two states, and the gradient of curvature across it is astronomically steep. This creates immense tension, a stress in the fabric of spacetime itself. Maintaining this sharp boundary is like trying to hold the edge of a knife perfectly still against a torrent of water. The universe naturally resists such severe, localized distortions. There is a constant pressure, a tendency for the sharp curvature to want to smooth itself out, to dissipate into the surrounding space and collapse the delicate bubble. The exotic matter scaffolding must exert a continuous, perfect counterpressure to hold this shape against the natural flow of geometry. It is a balancing act of cosmic proportions, where the slightest fluctuation in the distribution of negative energy could cause the entire structure to buckle or tear. The wall is not a static shell. It is a dynamic, high-tension membrane under perpetual strain, and its stability is the single most fragile element of the entire design. This extreme environment invites chaos from the quantum realm. The vacuum at such severe curvatures is not the quiet, frothing sea of virtual particles we discussed earlier. It becomes a storm. The intense gravitational gradients can polarize the quantum vacuum in unpredictable ways, potentially amplifying those fleeting virtual particles into real, high-energy phenomena. This is known as quantum instability. The negative energy density required to shape the wall might itself become unstable, boiling off into bursts of particles and radiation, or fluctuating wildly in density. These quantum fluctuations could act like microscopic tremors along the wall's surface. One moment, the negative energy holding a segment of the wall might flicker just slightly. In that instant, the catastrophic tension of the space-time curvature would have nothing to hold it back. That section of the wall could snap like an over-tightened guitar string. A rupture in the bubble wall would be a catastrophic event. The boundary separating flat interior space from the warped exterior would vanish at that point. The differing geometries would violently reconnect, likely releasing a focused jet of immense energy directly into the bubble's interior, or causing a cascading failure that unravels the entire warp field. The ship would be exposed not to the vacuum of space, but to a maelstrom of unraveling spacetime geometry. This transforms the bubble from a protective shield into a potential fragmentation grenade, with its own structural integrity as the primary threat. The fundamental challenge, then, is one of scale and control. We are attempting to impose a geometrically perfect, macroscopic order on a universe that is inherently fuzzy and probabilistic at its smallest scales. The bubble wall demands a sharp, clean transition, a perfect mathematical curve, but quantum physics tells us that at the Planck scale, the fabric of spacetime itself may be grainy and uncertain. Can a perfectly sharp boundary even exist in a quantum universe, or is it always slightly blurred, a statistical average rather than a razor edge? Maintaining coherence across this boundary means controlling energy densities and quantum fields with a precision we have never achieved for any object larger than a subatomic particle. We are asking to scale that control up to the size of a starship. It would require not just an understanding of gravity, but a complete theory of quantum gravity, a way to describe how spacetime itself behaves when it is both severely warped and examined at the smallest possible scales. The bubble wall sits at the intersection of our greatest theories, general relativity and quantum mechanics, and it demands they work together in a stable, engineered system. This is perhaps the deepest obstacle, one that goes beyond energy requirements and speaks to the very texture of reality. The universe may allow us to draw a warp bubble on paper, but its quantum nature might forbid us from ever carving that shape into the fabric of existence with the flawless precision the equations demand. The wall is where the beautiful geometry of the dream meets the noisy, uncertain bedrock of our cosmos. These energy conditions are not mere suggestions. They are the bedrock assumptions that keep the universe predictable. In the framework of general relativity, they are the rules that ensure matter and gravity behave in a sensible, classical way. The weak energy condition states that all observers, no matter how they are moving, will measure the energy density in their local region of space to be non-negative. In plain language, it means energy cannot be negative. You cannot have less than nothing. The strong and dominant conditions build on this, further ensuring that energy does not flow faster than light, and that gravity always remains an attractive force. These principles are what give our cosmos its stable, causal structure. They prevent bizarre scenarios like time machines made from negative energy or regions of space that spontaneously collapse into nothingness. They are the guardrails that keep the highway of physics from veering into chaos. When Alcubierre's warp drive requires exotic matter with negative energy density, it is asking for a direct, macroscopic violation of these core conditions. This is not a minor technicality. It is a fundamental challenge to the logical consistency of the universe as described by Einstein's theory. It suggests that to build the drive, we must first dismantle the very principles that make physics a reliable science. A universe where the energy conditions can be freely violated on large scales is a universe where prediction becomes impossible, where effects could precede their causes, and where the fabric of reality could become unstable. This is why the requirement for exotic matter is often seen as the ultimate deal breaker, a sign that the warp drive, while mathematically elegant, may be physically forbidden by the deep architecture of reality. Yet our story does not end here because general relativity is not the final word. It is a classical theory, magnificently accurate on large scales but silent on the quantum realm. The vacuum fluctuations and the Casimir effect we discussed earlier are quantum phenomena, and they already demonstrate that on microscopic scales, the energy conditions can be locally violated. Virtual particles represent a temporary borrowing of energy from the vacuum, a tiny, fleeting departure from the classical rules. This hints that the universe's accounting system is more complex than the classical conditions allow. The true frontier, then, lies in a theory of quantum gravity, a framework that will seamlessly unite the large-scale geometry of relativity with the probabilistic fuzz of quantum mechanics. Such a theory, whether it is string theory, loop quantum gravity, or something yet undiscovered, might completely redefine our understanding of energy and stability. It could show that the classical energy conditions are emergent properties, like the rigidity of a table that emerges from the chaotic motion of atoms. On our human scale, the table is solid, but at the quantum level, it is mostly empty space. Similarly, quantum gravity might reveal that the prohibition against negative energy is a large-scale approximation. It could provide a new set of quantum energy conditions that permit tightly regulated, microscopic violations, but prevent them from escalating into the macroscopic chaos that would break causality. In this future framework, exotic matter might not be a forbidden substance, but a highly constrained quantum state, a delicate pattern in the underlying fields that can only be sustained under specific, extreme conditions. The warp drive's feasibility would then hinge not on breaking the old rules, but on understanding the new, deeper rules that govern when and how space-time can be bent. The quest transforms from searching for a mythical material to decoding the universe's most fundamental operating manual, a manual that writes the laws for reality itself. The deepest challenge of the warp drive lies in a fundamental divide in our understanding of reality. For over a century, we have lived with two magnificent but seemingly incompatible rulebooks for the universe. General relativity paints the cosmos in broad, geometric strokes, describing how matter and energy curve the grand stage of spacetime. Quantum mechanics, in contrast, reveals a probabilistic, fuzzy world at the smallest scales, where particles flicker in and out of existence and certainty dissolves. The warp drive concept is born from the geometric elegance of the first rulebook, but it crashes directly into the quantum uncertainties of the second. Its most fragile component, that razor-thin bubble wall of extreme curvature, exists at the precise scale where both theories must apply, yet we have no unified law to govern it. This is the frontier of quantum gravity, and the future of any warp geometry depends entirely on what we find there. A successful theory of quantum gravity will not just add a new chapter to physics, it will rewrite the entire book, potentially redefining what is possible. It could reveal that the energy conditions we see as unbreakable laws are merely emergent properties, illusions of scale like the solidity of a table emerging from the chaotic dance of atoms. In this new framework, the vacuum of space is not a passive emptiness, but a dynamic, structured medium with its own fundamental graininess at the Planck scale, a length so inconceivably small that our current notions of smooth spacetime break down. The question becomes, can you sculpt a perfectly smooth, macroscopic warp bubble from a fabric that is, at its core, woven from discrete, vibrating threads? The answer will determine if the Alcubierre metric is a blueprint for a cathedral or a drawing of a castle in the clouds. Theories like string theory offer one possible vision of this deeper reality. In this framework, the fundamental constituents of the universe are not point-like particles, but incredibly tiny, vibrating loops or strands of energy. Spacetime itself may emerge from the collective behavior of these strings. From this perspective, the exotic matter required for a warp bubble might not be a strange substance you must find, but a specific, highly ordered state of these underlying strings and fields. It could be a coherent pattern of vibration, a standing wave in the quantum fabric that temporarily inverts the local curvature. The staggering energy requirements calculated using classical general relativity might be dramatically renormalized or rescaled when the full quantum gravitational effects are accounted for. The infinite peaks that appear in our current math could be smoothed away by the natural fuzziness of spacetime at the smallest scales. It is akin to calculating the strength of a material using only Newtonian physics, and then discovering that at the atomic level, quantum effects provide a flexibility and strength you never anticipated. String theory might show that creating a stable warp geometry requires not an impossible amount of negative energy, but an impossibly precise coordination of quantum states across the entire bubble, a symphony of vibrations where a single wrong note collapses the entire structure. The challenge shifts from a question of quantity to one of quantum coherence and control. Alternatively, loop quantum gravity approaches the problem from a different angle. It proposes that space itself is not continuous but woven from a network of finite loops, a spin foam of discrete volumes and areas. There is a smallest possible unit of space, a quantum of volume. In such a universe, you cannot curve spacetime arbitrarily sharply. The warp bubble's wall, which demands an infinitely sharp transition in the classical model, would hit a fundamental limit. You cannot compress space smaller than a Planck volume, and you cannot create a curvature gradient steeper than the network allows. This granularity imposes a new set of constraints, a cosmic resolution limit. It suggests that the perfectly smooth, mathematically ideal warp bubble of Alcubierre's paper is an illusion, a simplification that ignores the pixelated nature of reality. A real warp bubble, if it could exist, would have a wall with a minimum thickness set by the Planck scale, and its surface might have a subtle, foamy texture. This fundamental graininess could introduce stability, preventing the runaway quantum instabilities we fear, or it could make sustaining the coherent shape utterly impossible, like trying to build a perfectly smooth dome from irregular, lumpy bricks. The energy required might be dictated not by classical curvature, but by the cost of exciting the quantum geometry of spacetime itself into such an ordered, macroscopic configuration. From this quantum gravity perspective, the very act of forming a warp bubble becomes an experiment in the architecture of reality. It would test whether the universe's underlying code allows for such a drastic, localized recompilation of its own operating geometry. The Planck scale is not just a barrier to our understanding, it is a regulator. It may enforce a kind of cosmic censorship, preventing the formation of geometries that would lead to logical paradoxes or universal instability. The potential for closed time-like curves and causality violation, which haunts the superluminal warp drive, might be automatically resolved by quantum gravity. The theory could contain built-in mechanisms that cause any evolving spacetime geometry that threatens to form a time machine to become unstable and decay before the paradox can occur. In this view, the warp drive's greatest theoretical obstacle, its potential to break causality, might be its own salvation, a built-in safety switch that the universe provides. The drive might simply fail to engage in a paradox-inducing configuration, not because we are not clever enough, but because reality itself is structured to prevent it. This transforms the dream from a battle against physics to a negotiation with the deepest laws of existence. We are not trying to cheat the universe, we are trying to understand what kinds of magnificent structures it truly permits within its most foundational rules. The journey to the stars, therefore, may be waiting on a deeper journey inward into the quantum heart of spacetime itself. The allure of bending spacetime has proven irresistible, not just to physicists but to the engines of popular science. Headlines breathlessly announce warp drive breakthroughs with a regularity that belies the profound chasm between a mathematical exercise and a working engine. This sensationalism creates a distorted mirror, reflecting not the rigorous, obstacle-laden path of theoretical physics, but a simplified narrative of imminent conquest. The Alcubierre Metric, a dense piece of geometry demanding exotic matter and challenging quantum gravity, is often stripped of its essential warnings and repackaged as a blue sky promise. You might read that scientists have found a way to build a warp drive, when in reality they have published a paper exploring a subtle refinement of the energy requirements or a new simulation of its stability. These are vital, incremental steps in understanding, but they are not announcements of a prototype. The gap between a theoretical model and a physical device is cosmic, and popular coverage frequently collapses that distance into a single, exciting sentence. This does a disservice to the public's understanding and to the science itself. It frames the monumental, perhaps insurmountable, challenges of negative energy and quantum instability as mere engineering puzzles, soon to be solved by clever human ingenuity. In doing so, it risks turning one of the most profound ideas in modern physics into a disposable headline, another item on a checklist of future tech awaiting its turn. The real story is not about an imminent launch, but about a decades-long and likely centuries-long conversation with the fundamental laws of the cosmos. When we mistake a thoughtful what-if written in mathematics for a blueprint in a shipyard, we lose sight of the deeper, more meaningful journey. We replace the awe of confronting a universe that may forbid such shortcuts with the shallow satisfaction of assuming we will inevitably build them. This hype cycle can lead to a pendulum swing of public sentiment, from unfounded optimism to cynical dismissal, when the promised breakthrough does not materialize on schedule. The true value of the Alcubierre metric lies not in its promise of a starship, but in its power as a philosophical and mathematical probe. It forces us to ask extreme questions of our best theories. It reveals where general relativity strains against quantum mechanics, where our classical intuition about energy breaks down, and how the universe might protect causality from violation. Each paper that analyzes its stability, each simulation that models its formation, is not a step toward building a drive, it is a step toward understanding the boundaries of the possible. These studies are pressure tests applied to the framework of reality itself, searching for weak points, inconsistencies, or hidden doors, celebrating this rigorous, slow-moving inquiry as a series of imminent breakthroughs misses the point entirely. The warp drive concept is a lighthouse, not a harbor. It shines a beam onto the farthest, most treacherous shores of theoretical physics, illuminating problems we did not even know we had. Its legacy may not be an engine, but a deeper, more humbling map of the universe's ultimate rulebook, a map that shows us where the words "no trespassing" are written not in human language, but in the geometry of existence. While the mathematics of warp drives soars in theoretical abstraction, a small group of researchers dared to ask what it might feel like in a laboratory. The most notable effort was housed within a modest corner of NASA Johnson Space Center, an initiative often called Eagleworks. This was not a massive facility building prototype engines, but a small, advanced propulsion physics laboratory led by scientist Harold White. Its mission was to explore concepts at the very edge of known physics, including the possibility of measuring effects related to warp field geometry. The vision was breathtakingly humble in scale. The goal was never to warp a starship, but to see if one could detect, on a microscopic level, a signature of the physics that might one day make it possible. Imagine trying to hear the first note of a symphony by listening for the vibration of a single violin string from a mile away. That was the scale of the challenge. The experiments focused on an instrument called a white-Jude warp field interferometer. This sophisticated device was designed to pass laser beams through a carefully controlled region. The idea was to use a powerful electric field, generated by a device called a capacitor, to try and perturb the energy of the quantum vacuum in a specific way. If the negative energy effects required for a warp bubble had any microscopic, testable signature, this laser interferometer might detect an infinitesimally small change in the path length of the light, a whisper of spacetime distortion. The results, as shared in limited technical forums and papers, were deeply nuanced. Researchers reported observing anomalous signals, tiny shifts in the laser's interference pattern that seemed to correlate with the applied field. These signals were minute, at the very threshold of the instrument's sensitivity, and required immense care to separate from mundane sources of error like thermal expansion or electrical noise. The team was appropriately cautious, framing these not as evidence of a warp field, but as interesting anomalies worthy of further investigation. The sober context is essential. These signals were not proof of concept for a propulsion system. They were potential hints of a novel interaction between strong electromagnetic fields and the structure of the quantum vacuum, a phenomenon that might, in some distant theoretical framework, relate to the kind of energy densities a warp drive would need. The work was pioneering in its ambition to bring a science fiction concept into a measurable, experimental domain, but its scope was fundamentally microscopic and its findings preliminary. The Eagleworks lab, while a symbol of bold, institutional curiosity, operated with extremely limited funding and eventually ceased its public experimental work. Its legacy is not a breakthrough but a benchmark. It demonstrated that even our most speculative dreams can be subjected to the rigorous, if humble, discipline of measurement. It moved the warp drive conversation from pure theory into the realm of empirical questioning, where data, however faint, begins to whisper back. This shift from blackboard to lab bench, however tentative, marks a critical evolution in the story. It acknowledges that the universe's deepest secrets may not yield to thought alone, but must be gently probed, one delicate experiment at a time. The true power of a blueprint is revealed not when the building is finished, but when it is tested against the wind. For the Alcubierre Metric, this is its most profound contribution. It has become less a design for a starship and more a mathematical laboratory, a controlled environment where physicists can stress test the very foundations of general relativity to their breaking point. By constructing this precise geometric thought experiment, we gain a powerful lens to examine questions that are otherwise too abstract or extreme to grasp. How does causality, the unbreakable chain of cause and effect, enforce itself in a universe with flexible geometry? The warp drive model provides a clean, calculable scenario to explore this. By dialing the bubble speed past light speed in the equations, researchers can watch how the mathematics itself responds. They see the potential emergence of closed time-like curves, those paths that loop back on themselves. Studying this within the warp drive framework helps physicists understand the mechanisms the universe might use to prevent such paradoxes. Does spacetime become unstable? Do quantum effects erupt to destroy the geometry? The metric acts as a probe, sending a mathematical signal into the realm of superluminal motion and reporting back on the boundaries it encounters. In this way, the dream of faster-than-light travel becomes a tool for mapping the invisible fences that preserve the logical order of reality. It transforms a fantasy of propulsion into a serious inquiry into the architecture of time. The value shifts from engineering to epistemology, from building a machine to understanding the rules that may forever forbid it. This exploration extends to the very nature of gravity and energy. The metric's harsh requirement for exotic matter forces a deep confrontation with the energy conditions, those bedrock rules of classical physics. By demanding their violation, the warp drive blueprint highlights exactly where and why these rules exist. It pushes theorists to ask whether these conditions are absolute laws or emergent properties. Could a future theory of quantum gravity provide a new set of rules that allow for tightly regulated exceptions? The Alcubierre solution becomes a benchmark, a specific geometric shape against which any aspiring theory of quantum gravity must be measured. Can the new theory accommodate this shape without leading to nonsense or instability? If not, why not? The metric serves as a mathematical canary in a coal mine, testing the air in unexplored regions of physics. Its failures are as instructive as its successes, each calculated instability or infinite energy requirement marking a frontier in our understanding. We learn not how to build a warp drive, but where the solid ground of our current knowledge ends and the uncharted territory begins. This process elevates the idea from speculative gadget to a fundamental philosophical instrument. It allows us to conduct experiments in pure thought, manipulating the parameters of reality itself within the safe confines of an equation. We can ask, if we could curve spacetime this way, what would happen? The answers refine our intuition about the cosmos, teaching us about the relationship between geometry, matter, and the flow of information. The Alcubierre metric, therefore, endures not as a promise of tomorrow's technology, but as today's most elegant question. It is a conversation starter with the universe, a way of asking, in the most precise language we know, what is truly possible within the weave of space and time. The journey it inspires is inward, toward a deeper comprehension of the laws that bind the stars, and in that journey, we may discover horizons far more transformative than any shortcut to another galaxy. This confrontation with the universe's deepest rules forces a question of responsibility. If a society ever gained the power to bend spacetime itself, the implications would ripple far beyond engineering, touching the core of human identity and our place in the cosmos. The most immediate philosophical shock would be to our understanding of time. A functional warp drive, particularly one capable of superluminal travel, does not merely move a ship, it manipulates the stage upon which the drama of cause and effect is performed. The potential for closed time-like curves, those paths that loop back on themselves, introduces the specter of time travel paradoxes into sober reality. The classic grandfather paradox, where a traveler could potentially alter their own past, is not just a plot for fiction but a genuine logical crisis embedded in the geometry. This forces us to consider whether causality, the unbreakable sequence of past, present, and future, is a local convenience or a universal law. If the latter, then perhaps the universe has built-in safeguards through quantum gravity or other principles that make such paradox-inducing travel impossible, acting as a cosmic editor that deletes contradictory storylines before they can be written. The mere theoretical possibility, however, compels a profound humility. It suggests that our linear experience of time might be a fragile perception, not an absolute feature of reality, and that wielding such power would demand a wisdom we have scarcely begun to cultivate. Beyond the abstraction of time, the societal impact would be staggering. The sudden accessibility of the galaxy would trigger a transformation more profound than any in human history. The concept of distance, which has shaped every empire, economy, and culture, would become almost meaningless. A civilization with warp capability would not expand slowly across the void. It would appear everywhere at once from a human perspective. This raises urgent ethical questions about first contact, not with aliens but with ourselves. Would such a technology unite humanity under a common, stellar destiny, or would it amplify our divisions, allowing factions to simply drift apart into the infinite void, creating a diaspora so vast that shared history evaporates? The very notion of a homeworld changes. Earth becomes a birthplace, a point of origin, but not necessarily a center. This could foster a new cosmic perspective, a sense of being citizens of the galaxy, or it could lead to a profound existential loneliness, a realization of our smallness not just on a planet, but in an ocean of now reachable stars. The structure of society, from law to economics to governance, would have to be reinvented for a realm where the old constraints of geography no longer apply. This capability also casts a new and unsettling light on the Fermi paradox, the haunting question of why, if the universe is so vast and old, we see no evidence of other civilizations. A warp drive offers one potential answer, a so-called great filter that lies not in our past but in our future. Perhaps the technology to bend spacetime is not the gateway to the stars but a test. It may be that any species that masters it inevitably unlocks the power to alter causality or create destructive paradoxes, and in doing so, vanishes from the cosmic stage, either by destroying themselves or by becoming undetectable to those locked in linear time. Alternatively, a galaxy teeming with warp-capable civilizations might be a quiet one. If travel does not require crossing the intervening space, there would be no need for slow, visible generation ships or powerful radio signals announcing one's presence. Advanced societies might slip between the stars like ghosts, leaving no trace for our telescopes to find. This suggests a universe that is not empty but private, where the most profound technologies are also the most subtle, designed for minimal disruption to the fabric of spacetime itself. Our search for loud, obvious signals might be looking for the wrong thing entirely. Ultimately, the warp drive concept holds up a mirror to our own aspirations and limitations. It represents the ultimate expression of our desire to explore, to connect, to transcend the boundaries of our cradle. Yet its staggering requirements and profound risks reflect the universe's apparent insistence that such transcendence cannot be cheap or easy. If it is ever achieved, it would signify not just a technological triumph, but a philosophical maturation. It would mean we had learned to negotiate with the fundamental laws of reality, to understand the cost of a shortcut, and to accept the responsibility that comes with redrawing the map of existence. The journey to build such a thing may prove more valuable than the destination, for it forces us to ask not just how we can reach the stars, but who we must become to be worthy of that reach. In bending spacetime, we would ultimately be tested on our ability to bend our own nature toward wisdom, foresight, and a deep reverence for the delicate coherence of the cosmos we yearn to navigate. This silence from the cosmos is one of its most profound mysteries. We call it the Fermi paradox, a simple, haunting question asked by physicist Enrico Fermi decades ago. If the universe is so unimaginably vast and ancient, with billions of stars and planets, where is everybody? The apparent absence of galactic civilization suggests a sobering possibility that there might be something preventing life from reaching the stars, a series of cosmic filters. The immense challenge of the warp drive offers a compelling answer to this silence. Perhaps faster than light travel is not merely difficult, but fundamentally impossible in a stable, controlled form. The obstacles we have outlined, the need for exotic matter, the threat of quantum instability, the potential to shatter causality itself, might not be engineering problems to be solved. They could be universal safeguards, physical laws acting as a permanent barrier. This idea frames the Alcubierre drive not as a future technology, but as a test. It is a filter placed not in our past, but squarely in our future. A species may develop intelligence, master its planet, even reach out to its local star system. But when it finally confronts the geometry required to truly conquer distance, it might discover the universe says no. The energy conditions, the preservation of causality, the coherence of spacetime itself could be inviolable principles that no amount of cleverness can circumvent. The dream of bending spacetime might always remain a beautiful drawing on a page, a shape the cosmos simply will not allow to be built. In this view, the great silence is not empty, it is respectful. It is the quiet of a universe where the ultimate shortcut is eternally closed, ensuring that every civilization remains in its own stellar neighborhood, separated by the vast, peaceful moat of light years that also protects them. The galaxy would be full of islands, each with its own story, but with no bridges between them. This is a cosmic perspective that redefines the meaning of exploration. It suggests that the final frontier may not be about crossing the void, but about understanding and appreciating the sanctuary of our own corner of it. The drive to build a warp engine, then, becomes more than a technical pursuit. It is a way of probing the universe's deepest laws, of asking if the story of intelligence is one of eventual galactic connection, or one of profound and beautiful isolation. Yet for all its geometric grandeur, the warp drive remains a castle in the theoretical sky. Its path is blocked by fundamental questions about the substance of reality itself. Meanwhile, down on the solid ground of known physics, other avenues to the stars are being mapped, each formidable in its own right but operating within the universe's established rules. These are the engines of patience, trading the dream of instantaneous travel for the hard, slow work of crossing the void with the tools we are almost certain exist. Consider the fusion rocket, a concept that harnesses the same power that lights the sun. In principle, it would force hydrogen nuclei to fuse into helium, converting a tiny fraction of mass into a torrent of energy. This energy could be channeled through a magnetic nozzle to produce thrust. The efficiency would be staggering compared to today's chemical rockets, potentially enabling spacecraft to reach a significant fraction of light speed, perhaps 5 or 10%. Journeys to nearby stars would still take decades or centuries, but they would be conceivable. The challenge is not the physics of fusion, which we understand, but the engineering of containing a miniature star in a magnetic bottle small and light enough to fit on a ship and durable enough to run for years. It is a problem of materials, control, and scale, not of rewriting cosmic law. Then there is the solar sail, a technology of sublime simplicity. A vast, ultra-thin mirror would catch the pressure of light, itself photons streaming from a star or a powerful Earth-based laser. Each photon imparts a minuscule push, but over time, with no fuel to carry, a sail-equipped probe could accelerate to tremendous speeds. Breakthrough Starshot, a serious scientific initiative, envisions using a powerful laser array to propel gram-scale sails to 20% of light speed, reaching Alpha Centauri in just over 20 years. The sail itself represents a triumph of nanotechnology, needing to be meters across but only atoms thick, and able to withstand the ferocious laser blast. This is a technology of momentum and light, a gentle, continuous push across the gulf. It is slow, it requires immense patience, and it offers no return trip, but it operates on principles we can test and verify in a laboratory today. Perhaps the most potent concept within known physics is the antimatter rocket. When a particle of matter meets its antimatter counterpart, they annihilate completely, converting 100% of their mass into pure energy. This is the ultimate energy density possible under Einstein's famous equation. In theory, a rocket using antimatter as fuel could achieve speeds up to half the speed of light or more. The exhaust would be a beam of incredibly energetic radiation, providing thrust. The obstacles, however, are monumental. Antimatter is the most expensive substance imaginable to produce, currently requiring vast particle accelerators to create mere atoms at a time. Storing it is a nightmare, as it must be perfectly isolated from all normal matter in magnetic traps of immense precision. And even if these hurdles were overcome, the ship would need to carry equal amounts of matter and antimatter, making it a flying containment challenge of almost unimaginable difficulty. Yet, like fusion, it does not ask for new physics, only for an engineering mastery so advanced it seems like magic. What unites these concepts, fusion, sails, antimatter, is their shared language. They are all about propulsion. They focus on pushing a mass through space, on generating thrust to overcome inertia. They accept the tyranny of distance and the cosmic speed limit, and they seek to maximize performance within that cage. Their timelines are measured in human generations or robotic patience. The warp drive, in stark contrast, speaks a different language entirely. It is not about propulsion, but about geometry. It seeks not to push the ship, but to move the road. This distinction is categorical. One approach works within the universe's rulebook, striving to build a faster car. The other attempts to edit the rulebook itself, to redraw the map so the destination comes to you. The first is a marathon of engineering. The second is a revolution in understanding. Placing them side by side does not diminish either, but it clarifies the nature of the dream. The plausible engines show us a possible, if distant, future of slow boats between islands. The warp drive hints at a universe where the islands were never truly separate at all. If only we could learn to see the folds in the water. One asks how fast we can go. The other asks what space truly is. The silence of the cosmos is a question we are only beginning to learn how to ask. While the grand vision of a starship may lie generations away, the scientific pursuit of its underlying principles is more active than ever, charting a course through three distinct frontiers of inquiry. The first is the continued refinement of our digital laboratories, where numerical relativity simulations grow ever more sophisticated. Researchers are no longer content to model simple, steady-state warp bubbles. The latest simulations attempt to breathe dynamic life into these geometries, studying how a bubble might form from a ripple in flat spacetime, how it could be steered, and most critically, how it interacts with the complex environment of the real universe. These virtual experiments now factor in the interstellar medium, cosmic radiation, and the subtle influence of gravitational waves from distant events. Each simulation is a story, a what-if scenario played out in the universe's own mathematical language. They reveal not just if a bubble can exist, but how it would live and ultimately die, providing a crucial stress test for the concept's physical plausibility and highlighting the specific instabilities that any future theory must overcome. Parallel to this digital exploration is a deep dive into the foundational rules themselves through the study of alternative theories of gravity. Einstein's general relativity has passed every test with flying colors, but it is not necessarily the final word. Theories like modified Newtonian dynamics or scalar tensor theories propose subtle adjustments to how mass and energy curve spacetime. Researchers are now feeding the Alcubierre metric into these alternative frameworks, asking a pivotal question. Do these other theories make the warp drive easier or harder to achieve? Some proposals suggest that under certain modified gravity models, the exotic energy requirement might be reduced or the stability of the bubble wall enhanced. Others indicate the opposite, that the barriers become even more severe. This line of inquiry is invaluable, not because it promises a quick path to a warp drive, but because it uses the warp drive as a diagnostic tool. The metric's extreme sensitivity acts like a litmus test for gravity itself. If an alternative theory cannot consistently accommodate the warp geometry without producing nonsense like time travel or negative probabilities, that theory itself may be flawed. In this way, the dream of faster-than-light travel serves as a sharpening stone for our understanding of the fundamental force that shapes the cosmos. Perhaps the most intriguing frontier looks not to the future but to the present sky, searching for evidence that the universe is already performing this geometry. Astronomers and astrophysicists are beginning to ask if there are any natural phenomena that might resemble, even faintly, a warp-like spacetime structure. Could certain energetic events, like gamma-ray bursts or the collisions of ultra-dense objects, create transient, localized distortions that share mathematical features with an Alcubierre bubble? The focus is not on finding alien starships, but on discovering if the laws of physics, under conditions of extreme energy and density, naturally twist spacetime in ways that echo our blueprints. Furthermore, the search extends to cosmology, the accelerating expansion of the universe, driven by the mysterious influence of dark energy, involves a kind of stretching of spacetime on a cosmic scale. While entirely different in mechanism and purpose, it demonstrates that spacetime geometry is not static. It is a dynamic, evolving entity. Studying these vast, natural processes could yield insights into the principles of manipulating geometry on a smaller, more controlled scale. The goal is to find a natural analog, a cosmic example of a spacetime shortcut, however wild or unstable, to prove that such geometry is not just a figment of human imagination, but a possible, if rare, stitch in the fabric of reality. This transforms the quest from pure invention to one of discovery, suggesting that if we look closely enough at the universe's most violent and beautiful events, we might find the fingerprints of the very physics we seek to one day command. The journey through the mathematics and physics of warp drives leads us to a clear, if sobering, vantage point. Today's scientific consensus views the Alcubierre metric with a profound duality, a blend of deep admiration and grounded skepticism. It is widely recognized as a valid and ingenious solution to Einstein's field equations, a masterclass in theoretical physics that proves such geometry is not forbidden by the rules of relativity. Its true value lies not in offering a blueprint for a starship, but in acting as a precise diagnostic tool. It has clarified with mathematical certainty the exact physical cost of bending spacetime for propulsion. The metric has itemized the bill for a cosmic shortcut, and the total is staggering. It demands a form of energy that violates long-held principles of classical physics, requires control over quantum phenomena at a scale we cannot fathom, and threatens the logical flow of causality itself. With our current understanding of matter, energy, and the structure of the vacuum, this cost appears not just prohibitively high, but likely unphysical. It suggests the universe may have built-in safeguards, principles woven into the quantum fabric of reality, that prevent such drastic geometric manipulations from being stably assembled. So the consensus is not a dismissal, but a reframing. the warp drive is no longer seen as an engineering challenge awaiting better materials, but as a profound philosophical probe. It is a mathematical thought experiment that illuminates the boundaries of the possible, teaching us where our current theories of gravity and quantum mechanics collide, and what profound mysteries await a deeper, unified understanding of reality. The state of the art tells us that the path to the stars, if it exists, will not be found by bending the rules we know, but by discovering the new ones we have yet to write. The Alcubierre Metric's true gift was a translation. It took a dream spun from starlight and science fiction and rendered it into the precise, unforgiving language of the cosmos, the mathematics of general relativity. In doing so, it performed a service far greater than providing a starship blueprint. It gave us a ruler, and with it, we measured the chasm between a beautiful idea and physical reality. The exercise revealed not a failure of imagination, but the breathtaking scale of the universe's own rulebook. To even contemplate bending spacetime is to engage with forces that govern black holes and the birth of galaxies, to wrestle with questions about the nature of time, energy, and causality itself. The metric mapped the dream, and in that map we saw the towering, perhaps insurmountable, mountains we would need to move. This is not a story of disappointment, but one of clarified awe. It shows that our most ambitious fantasies, when subjected to the rigor of physics, become probes sent into the deepest unknown. They become questions asked of the vacuum, challenges issued to the fundamental constants. The legacy of this work is not a faster-than-light engine in a hangar, but a transformed conversation. It has moved the warp drive from the realm of pure fantasy into a sustained, serious dialogue within theoretical physics, a dialogue that continues to push the boundaries of what we think we understand about gravity, quantum fields, and the structure of reality. This ongoing inquiry, this relentless testing of the universe's limits with mathematics and simulation, is itself a form of exploration as profound as any voyage between the stars. It reminds us that the ultimate adventure does not always require a rocket. Sometimes it begins with a piece of chalk, a clean slate, and the courage to write an equation that asks the universe for its secrets. The final frontier, it seems, is not just out there among the distant suns, but right here, in the silent, elegant struggle to comprehend the fabric that holds them all.